It's surprisingly interesting how few things we need in order to get encryption going, to understand how cryptography works. In this short video, we'll investigate the division algorithm. And this is something you've seen before. It's not really an algorithm at all. It's more of a theorem. And it says that if A is any integer and D is a positive integer, then there are unique integers Q and R where R is going to be as small as 0 but as big as D, or smaller than D, such that A is equal to D times Q plus R. Now, if you think about what Q and R represent, Q is the quotient and R is the remainder. So the quotient is basically how many times D goes into A. And the most basic example, or one basic example that we could give is, let's say we try to take 7 and we try to divide it by 3. Okay, so I'm going to say that A is 7 and D is 3. Okay, well, how many times does 3 go into 7? How many times can we remove 3 from 7? Well, we can do it 2 times. So we can multiply this by 2, and that's the most number of copies, or the greatest number of copies of 3 that we can subtract from 7. 7 minus 3 is 4, minus 3 is 1, and that leaves me with a remainder of 1. So 7 is equal to 3 times 2 plus 1 creates a true statement where Q is called the quotient. That's the number of times this value D goes into this value A, and then it leaves a remainder of 1. The only restriction is that that remainder has to be between 0 and, in this case, 3. Well, if it's, or excuse me, 0 and 2, it can't be as big as 3. And that kind of makes sense, because if this number was 3, then that would mean that we could remove one more copy of 3 from 7. But with a remainder of 1, there's no, we cannot remove 3 from 1 any number of times without getting into negative integers, and we don't want that. Another example would be, say, 8. If A was 8 and Q or D was 2, well, in fact, in this case, we could extract exactly 4 copies of 2. We could subtract 2 from 8 a total of 4 times, and that would leave me with a remainder of 0, which again is a totally valid statement. We have to make sure that the remainder is somewhere between 0 and D minus 1. It can't be as big as D, it has to be less than D. To come up with other examples, 9 is equal to, let's see, 5. Okay, well, how many times can I subtract 5 from 9? Well, I can do it 1 time, and that leaves me with a remainder of 4. And 4 is definitely a value that is between 0 and, I think I've mixed these up. I should say 5 times 1, because D is 5. That can go into 9 1 time, and it leaves me with a remainder of 4. So 4 we can see is definitely between 0 and less than 5. And so this is essentially the division algorithm, and we can reason through this by kind of saying, well, D can go into A an integer number of times. Perhaps that's 0 times. And then whatever is left over is the remainder. However many times D goes into A is Q times, where Q is some integer. What about negative values? Well, we've said A is just some integer. So what if A is negative 5? And what if D is equal to 3? So D has to be a positive integer. Well, if D is 3, then we may be able to say that Q in this case is negative 1. I'll write that in parentheses. And if that were the case, then 3 times negative 1 is negative 3, and that means that my remainder would have to be negative 2. 3 times negative 1 is negative 3, plus negative 2 is negative 5. But wait a minute, this violates what we're saying. We're saying that the remainder has to be non-negative. It has to be between 0 and smaller than the value of D. So negative 1 is actually not a valid quotient, and negative 2 is actually not a valid remainder. And this is where the idea of unique comes in. There's only one, I held two fingers up, but just one possible value for Q and for R. So instead of using -1, what I can do is I can say this is -2. 3 times -2 is -6. And then to make -6 into -5, I would have to add 1. And that is valid because 1 is certainly a value that's between 0 and 1 less than 3, which is 2. So we just have to make sure that our remainder is positive. So that is an element of the integers, but it's a positive number. So we'll often put this sort of superscript of plus above that integer sign to indicate that it needs to be positive. Now, a couple of brief things of notation. In this equality given in the division algorithm, d is called the divisor. Right? So d is the number of is the thing that is we're extracting from our value of a. A is called the dividend. That is the quantity that's being divided. Q is called the quotient. That's the number of times that d goes into a evenly, or at an integer number of times. And R is called the remainder. This notation is used to express the quotient and remainder. Q is equal to A div D. Okay, so in this example up here, we could say that 2 is the quotient of 7 divided by D, which is 3. In other words, 2 times 3 is 6. That's the number of times that we can extract 3 from 7. The remainder is written as A mod D, and the remainder in this case is 1. So 1 is the remainder of what you get when you take 7 divided by D, which in this case is 3. So if you take 7 divided by 3, you get a quotient of 2, but a remainder of 1. We can say a similar thing up here. We can say that Q, our quotient up here was -2, is equal to A div D. So A was -5. -5 divided by 3 gives me a quotient of -2. So 3 goes into -5 -2 times. And it's kind of a weird thing to say. But then we could also say that the remainder, which is 1 is the remainder of A, -5, mod D, which is 3. So if you take -5 divided by 3, you get a remainder of +1. And again, that's kind of where this number theory thing gets a little bit strange, because divisibility by negative numbers is not something we often want to do. And in cryptography, the good news is we're always dealing with non-negative integers.